So now that we've got our basic ideas down, let's see some actual examples of evaluating some antiderivatives, some indefinite integrals. So our first example here says evaluate the integral of 7x to the fifth minus 5x to the fourth plus 6x squared minus 14x plus 3 dx. Alright, so the first few times you might want to go through this very carefully. And so what I would do is say, well then this is equal to, using some properties, this is equal to 7 times the integral of x to the fifth dx minus 5 times the integral of x to the fourth dx plus 6 times the integral of x squared dx minus 14 times the integral of x dx plus the integral of 3 dx. Alright, so then 7 times, now the antiderivative of x to the fifth, since this is a power, I'd increase the power by 1 and divide by the new power. X to the sixth over 6, plus a constant. Okay, but there's going to be other constants, so remember, we can just add one constant at the end. Minus 5 times x to the fourth, the antiderivative of x to the fourth would be x to the fifth divided by 5. Plus 6 times the antiderivative of x squared is x to the third over 3. Minus 14 times, now this x we understand is an x to the first. So then this would give us minus 14 times x squared over 2. Plus, now the antiderivative of a constant is the constant times the variable, times the x. So then plus 3x plus a constant. Now we would then clean this up a little bit. 7, this is a 7 over 1. So I have 7 times x to the sixth over 6. I would write 7 sixths x to the sixth, 5 over 5, minus x to the fifth, 6 over 3, plus 2x cubed, 14 over 2, minus 7x squared, plus 3x, plus c. And so that's what I would write as the integral. Our next example has some negative exponents. That's okay. Negative exponents are fine. They work just the same, except for that one situation, which we'll see later on. So again, then this would be 10 times the integral of z to the negative sixth dz, plus 8 times the integral of z to the negative fifth dz, minus the integral of z to the negative second, plus the integral, I forgot the dz, plus the integral of 1 dz. Alright, now be careful here. Negative exponents, but if we increase by 1, really there's sort of a subtraction idea there. So then this would become 10 times z to the negative fifth over negative 5. Negative 6 plus 1 is negative 5. Plus 8 times z to the negative fourth over negative 4 minus z to the negative first over negative 1 plus the antiderivative of 1 is 1 times z plus a constant. Alright, so again, cleaning this up then, I'd have negative 2z to the negative fifth minus 2z to the negative fourth plus z to the negative first plus z plus a constant. Now this next example, I have the integral of the 7th root of w squared plus 3 minus 9 times the cube root of w to the 7th dw. Alright, well, first thing I would do is rewrite this so I can put it in a form that I understand. I have the power rule for antiderivatives, so I've got to get these written as powers. So then this is equivalently written as the integral of w to the 2/7 dw minus the integral of 3 dw minus 9 times the integral of w to the 7/3 dw. All right, so now using our power rule in reverse, right, our antiderivative power rule, I would have to increase the 2/7 by 1. Well, 2/7 plus 1 is 9/7. So I'd have w to the 9/7 divided by 9/7 minus 3 times w minus 9 times w. Now 7/3 plus 1, well 1 is 3/3, so 7/3 plus 3/3, w to the 10/3 over 10/3 plus a constant. And then cleaning this up a little bit, I would write 7/9 dividing by 9/7 is the same as multiplying by 7/9. 7/9 w to the 9/7 minus 3w. Now 9 divided by 10/3 is 9 times 3/10, so minus 27/10 w to the 10/3 plus a constant. Now, one thing that you should always remember with these is on any of these exercises where we're asked to find an antiderivative, I should be able to check my work by differentiating. Let's take the second example. Let's find d by dz of that expression. Let's find d by dz of this expression. And so then I would have -2 times -5z to the -4th minus 2 times -4z to the -3rd. Oops, -5th. I did my subtraction wrong there. Oh, I did my subtraction wrong on both of them. That's no good. Let's try this again. Through the first term, I would have -2 times -5z. Now, -5 minus 1, the exponent minus 1 is -6. Minus 2 times -4. Z to the -4 minus 1 is -5. Plus -1, z to the -2nd, plus 1, plus 0. The derivative of a constant is 0. And if we simplify this, we get back to the original expression, 10z to the -6th plus 8z to the -5th minus z to the -2nd plus 1. And that was the original integrand. So always remember that you can check your work on these. You can check your work on any antiderivative by differentiating and maybe using some algebra. Let's see some more examples. So what I'd like for you to do with these three is to pause and try each of them on your own. And what you're going to need to do first with each of these, none of these are in a form that we know how to work with right now. For each of these, you're going to have to do some algebraic manipulations before you actually find the antiderivatives. So now would be a great time to pause and try these on your own. Well, I hope you paused to try these. Generally speaking, we learn the most when we do things ourselves, not from watching other people. All right, so what I would do with this is, I've got to get these each into a form. I've got to get this expression. I've got 6 over y cubed minus 1 over 7y to the 6th plus 1 over y squared plus 1 over the cube root of y to the 5th. I've got to get these into the forms of powers. This can be written equivalently as 6, the integral of 6y to the -3rd minus 1/7 y to the -6th plus y to the -2nd plus y to the -5/3 dy. All right, and now I won't break this up into the multiple integrals like I've been doing in the past examples. We should hopefully understand the basic concept there. All right, so then what I would get from there is I'd have 6 times y to the -2nd over -2 minus 1/7 times y to the negative fifth over negative 5 plus y to the negative first over negative 1 plus y to the negative 2/3 divided by negative 2/3 plus a constant. So then this gives us, let's clean this up a little bit, negative 3 y to the negative second plus 1/35 y to the negative fifth minus y to the negative first minus 3/2 y to the negative 2/3 plus a constant. And there's the antiderivative. All right, now we have the integral of x to the sixth times 1 minus 4x squared plus x cubed dx. One thing to be very careful about. We are not allowed to write this as the integral of x to the sixth dx times the integral of 1 minus 4x squared plus x cubed dx. It just doesn't work. Just like when we were differentiating, we couldn't just differentiate the first factor, differentiate the second factor, and multiply them. There was a special product rule. Similarly, there isn't a special we can't just take the product of the integrals of the factors. It just doesn't work. All right, so don't do this. Instead, distribute. This is the integral of x to the sixth minus 4x to the eighth plus x to the ninth dx. So then that would be 1/7 x to the seventh. Sorry, let me be careful. I haven't really used that idea. All right, so that would become x to the seventh over 7 minus 4 times x to the ninth over 9 plus x to the 10th over 10 plus a constant. And you can verify this, that if you tried what I did in red, you would not get the same expression as what I did in blue. And so then if we clean this up a little bit, I would write 1/7 x to the seventh minus 4/9 x to the ninth plus 1/10 x to the 10th plus a constant. Right, so notice what when I first went through this exercise, I said, okay, the x to the sixth gives us 1/7 x to the seventh. The antiderivative is 1/7 x to the seventh. I went straight to that form just from experience. I've done this so many times. I know to write it like that. All right, similarly here, the integral of 7 minus 9u squared. Let's first use some algebra. Let's multiply this out. This would become the integral of 49 minus 63 plus 63 is 126 minus 126 u squared plus 81 u to the fourth du. And so then this becomes 49u minus 126. All right, let's write this. 126 times u to the third over 3 plus 81 times u to the fifth over 5 plus a constant. Maybe clean this up a little bit. I would write 49u minus 126 divided by 3. That's divisible. 126 divided by 3 is 42 minus 42u cubed. 81 over 5, that's not divisible. I would just leave the fraction. 81/5 u to the fifth plus a constant. And that's what I would write. All right, so all of those examples in these first two slides were really all just powers. Let's get some experience with some other types of antiderivatives. All right, so this first example here, we have the integral of 8x to the fifth minus 2x cubed plus 7 over x squared dx. Now, just like there isn't a product rule for integrals, there isn't a quotient rule for integrals. So I'd like for you to pause, try this one out on your own, and see if you can use some algebra first to get this to a form that we can work with. All right, so what I would do first is think, well, this is the same as, since I'm dividing, right? Division is the distributive property. We can think of the distributive property. This is 1 over x squared times the 8x to the 5th minus 2x cubed plus 7. And so I can think of this as the integral of 8x to the 5th over x squared minus 2x cubed over x squared plus 7 over x squared. You know, just how we add fractions backwards. And so then this becomes then the integral of 8x cubed minus 2x plus 7x to the negative second dx. And so now that's in a form that I can work with. It's all in powers. So then this becomes then 8 times x to the 4th over 4 minus 2 times x squared over 2 plus 7 times x to the negative 1st over negative 1 plus a constant. And we clean this up a little bit. We get 2x to the 4th minus x squared minus 7x to the negative 1st plus a constant. So that's how I would write it. The next example, the integral of 8 cosine theta minus 3 cosecant theta cotangent theta d theta. This should be a fairly straightforward use of some of the basic forms we learned in the first video for this topic. So why don't you pause and try this one out. All right, with just a little bit of manipulation, I can think of this as 8 times the integral of cosine theta d theta minus 3 times the integral of cosecant theta cotangent theta d theta. All right, so now in the previous video, we saw the integral of cosine x dx. It's just cosine theta d theta. So what? It's a different variable. The same concepts apply. It's a dummy variable. We can use whatever variable we want. The concepts are the same. So the integral of cosine theta, the antiderivative of cosine theta, is the sine function, sine theta. So I'd have 8 times sine theta minus 3 times, now the integral of cosecant theta cotangent theta, that was negative cosecant theta plus a constant. Let's clean this up a little bit. 8 sine theta. We wouldn't write minus and negative, we write plus 3 cosecant theta plus a constant. Now this next example is a little tricky. What I would suggest is use a concept from the first exercise on this page. Use that division concept, and then you'll also need to use some trigonometry to help you with this one. But now would be a good time to pause to try this one out on your own. All right, so the first thing that I'll do here is I'll say, well, cosine cubed theta over cosine square theta, I can simplify that. And then sine theta, or t instead of theta, sine t over cosine square t, I can do something with that as well. So if I use a little bit of manipulation, this becomes the integral of cosine cubed t over cosine square t plus sine t over cosine square t dt. Now it might be tempting to think of that cosine square, to put that in terms of sines by using a Pythagorean identity. But that's not the right idea for this one, unfortunately. All right, so what I'll do now is say, well, that's the same then as the integral of cosine t. All right, cosine cubed t divided by cosine square t is cosine t. And now I'm going to think of the second term here. I'm going to break up that cosine square as a cosine times a cosine. I'm going to think of that sine t as a sine times 1. So I've got a sine t times 1 over a cosine t times a cosine t, right? And then we have dt. And now if I look at these two, if I think of these factors separately, I've got sine t over cosine t, and I've got a 1 over cosine t being multiplied. And if you remember a little bit from trigonometry now, this is the integral of cosine t plus tangent t secant t dt. And so then this becomes, well, the antiderivative of cosine t is sine t, and the antiderivative of tangent t secant t, well, we saw that in the previous video. I just wrote the secant factor first, and so then this is sine t plus secant t dt. Oh, not dt, sorry, plus a constant. Okay, so a little bit of algebraic manipulation, and then we had to remember a couple of trig identities. All right, let's look at a few more examples here. We have the integral of e to the z plus 3 over z dz. Again, now would be a good time to pause and try this one out. All right, so this one's not too bad. I can think of this as the integral of e to the z plus 3 times 1 over z dz. The antiderivative of e to the z is easy. It's e to the z. The antiderivative of 1 over z is the natural log of the absolute value of z. So then this becomes e to the z plus 3 natural log absolute z plus a constant. Now the next example, this one's not straightforward. Now remember, we don't have, there's no product rule for integrals, and we haven't seen how to deal with e to the negative u. We haven't seen how to deal with e to the 2u. So I'm going to have to use some algebraic properties here. Let's apply the distributive property first. This becomes then the integral of e to the negative u times e to the 2u plus e to the negative u times e to the u du. All right, now, if we remember some algebra, e to the negative u times e to the 2u, that becomes the integral of e to the u. If we're multiplying factors with the same base, we add exponents. Plus e to the negative u times e to the u is e to the 0 du, and if you remember, e to the 0 is 1. So this becomes the integral of e to the u plus 1 du, and so then that's e to the u plus a constant. And this last example is fairly straightforward. The integral of 1 is easy to find. The integral of w squared is relatively easy to find now. And just remembering that if we have this 1 over 1 plus w squared, no algebra is needed. This is a special form. This gives us back the arctangent. So then this is fairly straightforward. This becomes w plus 1/3 w squared, w cubed, excuse me, plus tangent inverse of w plus a constant. So those were some straightforward examples of how to find antiderivatives. Believe me, it's going to get much more complicated. It's going to get somewhat more complicated later on in this course, and then in Calculus 2, it gets much more complicated, and we learn some other techniques. Let's see a couple of applications. How can we use these antiderivatives? So here we're told to determine p of t if p prime of t is 6e to the t minus 4 minus 10t. Determine the function given the derivative of the function, and then we're given this condition. we're told that P of 0 is 7. Now really, what we're doing here is solving a differential equation because we're given the derivative and we're trying to find the original function. We're solving a differential equation. I mean, of course, now this is a fairly simple example of a differential equation. We get into much more complicated examples in later courses. But here's what I would understand. I know that P of t would be the integral of P prime of t dt. So then P of t would be the integral of 6 e to the t minus 4 minus 10t dt. So finding the antiderivative of 6 e to the t, that would be 6 e to the t. The antiderivative of the minus 4, that would be a minus 4t. The antiderivative of the 10t, that would be minus 10 times t squared over 2 plus a constant. So P of t is 6 e to the t minus 4t minus 5t squared plus a constant. Now, we know that P of 0 is 7. See, this is a condition. This P of 0 equals 7. We need to now use this condition to find the appropriate value of C. So now if P of 0 equals 7, now remember what that means is when t is 0, P of t is 7. So 7 must be equal to 6 e to the 0 minus 4 times 0 minus 5 times 0 square plus a constant. 7 must be equal to 6 times 1 minus 0 plus a constant. We go through a little bit of arithmetic here, and C must equal 1. So now we take that back over and revise our model, revise our solution. And so then I would state then that P of t is equal to 6 e to the t minus 4t minus 5t squared plus 1. This is the specific antiderivative that meets the given condition that P of 0 equals 7. Right? There's a general antiderivative. We found the general antiderivative with the plus c. This is the specific antiderivative that also meets the given condition. Let's see one more application. So it's known that the acceleration due to gravity is approximately negative 32 feet per second square. It's actually negative 32.2, I think, but that's good enough for our purposes. Suppose a rock is thrown upward from an initial height of 6 feet above ground with velocity of 90 feet per second. When will the rock hit the ground? So this is an example of a problem we might see in physics. And in physics, maybe you were just sort of given some formulas to use for this. In calculus, we can derive the formulas using what we've just learned. All right, I know that the acceleration is constant. I know that the acceleration due to gravity is negative 32 feet per second squared. I know from what I've learned with differential calculus, with derivatives, I know that the acceleration is the derivative of the velocity. So, going backwards then, the velocity function, I could have called this a of t, right? The velocity function would then be the integral of negative 32 dt. So then the velocity function is negative 32t plus a constant. Now, the rock is thrown upward from an initial height of 6 feet above ground with a velocity of 90 feet per second, and it's thrown upward. I know that V of 0 is 90. Substituting that in, all right, so I know that v of 0 is 90, so that means that 90 must be equal to negative 32 times 0 plus c, therefore c is 90. So that means then that my velocity function, v of t, is negative 32t plus 90. Now I can use that to find my position function. The position function, let's use s. S of t would be the integral of the velocity function. The integral of negative 32t plus 90 dt. So that would be negative 32 times t to the second over 2 plus 90t plus a constant. Let me use a different letter. Let me use d instead of c. So then my position function s of t is then negative 16t squared plus 90t plus d. Now I know that the ball was thrown upward from an initial height of 6 feet. That means that the position at t equals 0 must have been 6. Substituting that into our position function, that means then that 6 must be equal to negative 16 times 0 squared plus 90 times 0 plus d, and so then d must equal 6. Revising. So my position function, s of t, must then be negative 16t squared plus 90t plus 6. When will the rock hit the ground? When will the rock hit the ground? Well, the rock hits the ground at height 0, at position 0. So now solve s of t equals 0. Negative 16t squared plus 90t plus 6 is 0. I'm not even going to try to figure out if this factors. I'm going to go straight to the quadratic formula. T equals negative 90 plus or minus the square root of 90 squared minus 4 by negative 16 by 6 over 2 times negative 16. All right, and we calculate these values. Bring up my calculator here. Negative 90. I always do the minus first, doesn't really matter. Square root 90 squared minus 4 by negative 16 by 6. Close off the radical, close off the numerator, divide by negative 32. And let's check plus. Alright, so I get two values. I get that t is approximately negative 0.066 seconds. And t is approximately 5.691 seconds. Realistically, when can the rock hit the ground? It can't hit the ground in negative time. So at 5.691 seconds is when the object hits the ground. And these are just a couple of examples of how we can use antiderivatives, how we can use integrals. The next couple of sections introduce a really important concept, and really what led to the development of the concept of the antiderivative and of the integral. And so we'll build that idea in the next section.